In today's lesson, we are going to be looking at solving equations using logarithms. So just to review a couple of things that we've looked at so far, we've looked at how to convert between the exponential form. We see here y equals b to the power of x. We've learned how to convert that into the logarithmic form, which is x is equal to log base b of y. We've learned some of the properties of logarithms. So one of the ones that we looked at previously was that log base 10 of a to the power of b can be rewritten as b times log base 10 of a. And the reason I'm saying base 10 is because it's implied that if we don't see a base for our logarithm, we can assume that it's 10. And another one is log base a of b is equal to log base 10b, or base 10 of b, divided by log base 10 of a. And so if we have a logarithm with a different base other than 10, we can rewrite it in terms of logarithms with base 10. And the only reason we do that is because on our calculator, we only have a log button. We only have a button for log of base 10. So we can't solve it with a calculator if we have other bases, aside from using our general knowledge of powers, which we did previously. So just in general, let's just go through and calculate. So we're just going to write or type these into our calculator, just get an answer. So if I do log base 10 of 8, I get 0.903. 0.903. So essentially that would be the same thing as saying 10 to the power of 0.903 would equal 8. Log of 64, 1.806. 2 times log base 10 of 8 is 1. No, that can't be right. Same thing. No, that is 1.806. Log base 3 is 0.477. Log base 10 of 27 is 1.431. And 3 log base 10 of 3 is 1.431. So we should notice that these two values are the same. And that is because it's using this property here, where if this was this 2 could actually be the exponent. So this could be rewritten as log base 10 of 8 squared, or 64, except we bring the 2 out front. Same with down here, this could be rewritten as log base 10 of 3 to the power of 3, which is 27. So just showing how the different properties apply, because this property is what we're going to be using when trying to solve exponential equations using logarithms. So for example, let's try to solve 3 to the power of x equals 100. Can it be done using common bases? In this case, no. We can't rewrite 10 as a power with base 3. So we can't solve this not with common bases. There is a way that we can solve it though, and we're going to be able to solve it using logarithms. So the steps to solve it using logarithms, and there are going to be 3. The first step is we are going to take the log of both sides. So similar to how if we change anything in an equation, we have to do it to both sides. Otherwise, we change the equation entirely. Right? So in this case, we're going to take the log of both sides. So that's going to allow us to do that because it's going to keep our equation balanced. Next, we're going to use the exponent rule of logs. So the exponent rule of logs would be this one here. That's the law that we're going to be using. And then 3, we're going to isolate for x. So we're going to solve for x. So let's go through that with this equation. So we're going to start with 3 to the power of x is equal to 100. Again, I can't solve this using common bases, so I'm going to use logarithms. First, I'm going to take the log of both sides, so log 3 to the power of x. And again, it's implied that every log that we take here is going to be base 10. And that is going to equal log of 100. So I haven't changed my equation because I've done the same thing to both sides. Even though it looks different, technically I haven't changed the equation. Now I'm going to use my exponent rule. So that tells me that this exponent of x is now going to come down in front, and it's going to be x times log 3. This is still going to equal log of 100. Nothing's changed over there. There's no rule that we have to use. But now I can start to solve for x, because if I do log of 3, right, that's just a number. We saw that previously up here, that it was just a number. So I can divide this entire side by log 3, and I can divide the other side by log 3 to keep things balanced like we want to do. And I get x is equal to, one side would cancel out, and when I solve log 100 divided by log 3, I get 4.19. So this log 100 divided by log 3, that's just something that we do on the calculator. Right? And we get 4.1. So then if we do 3 to the power of 4.19, we should get 100. We should get relatively close to it. If we do 3.1 or 3 to the power of 4.19, we get 99.801. But if we kept more decimal places, it would be exactly 100. So that is how we solve using logarithms when we can't use common bases. So let's go through and just practice doing it a few more times. So 12 to the power of x is equal to 250. Again, we can't use logarithms, or we can't use common bases, so let's use logarithms. We're going to take the log of both sides. So log 12 to the power of x is equal to log of 250. On the one side, I can use the exponent rule. So x log 12 is equal to log 250. I'm going to divide both sides by log 12 because that is just a number. So I'm going to treat it as such. X will then equal log 250 divided by log 12, which we get is 2.22. Which would be our final answer. So 12 to the power of 2.22 would give us 250. Again, approximately depending on how much we rounded our answer. Even if we have a difficult exponent like x plus 3 instead of just x, we can still do the same thing. The same thing still applies. Right? So I'm going to take the log of both sides. So log 5x plus 3 equals log of 1,000. So this entire exponent, this x plus 3, this entire exponent is coming down in front based off of the exponent rule. So it's x plus 3, because that's the entire exponent, times log 5 is equal to log 1,000. I'm going to divide by log 5 first. One side will cancel out. We'll end up with x plus 3 is equal to 4.29. Now I'm going to again work to isolate x. So I'm going to subtract 3 from both sides, right? Solving equations. X is equal to 1.29. So again, treating it like an equation after we cancel out the bases using logarithms, similar to when we use common bases in a sense. Except we're using logarithms to help us cancel out those bases. The next one, 3 times 8 to the power of 2x minus 3 is equal to 150. So again, this is again similar to maybe what we might find in an exponential function, right? We have an a value, we have a ratio, and then we have an exponent. In this case, we want to get our power alone first. So I want to divide everything by 3 to get rid of that 3 that we're multiplying initially. I'm going to divide the other side by 3. We have 8 to the power of 2x minus 3 is equal to 50. So now that I have one power equals something or equals a value, now I can set logs to both sides. So log 8 to the power of 2x minus 3 is equal to log of 50. Use my exponent rule. The 2x minus 3 comes down in front to multiply log 8. Same as saying log of 50. Now I'm going to work to isolate my x. I'm going to divide both sides by log 8. Treating it just as a value. 2x minus 3 equals 1.88. I'm going to cancel out the separate term first. So I'm going to add 3 to both sides. 2x equals 4.88. Now to get x by itself, we divide both sides by 2. And we get now x is equal to 2.44 approximately, because we've rounded a little bit when we divided our logarithms. So similar to solving with common bases, right? We kind of want to get rid of the base of our power, so to speak. In this case, we can't use common bases just based off what the numbers are. So we're using logarithms to cancel out the bases, and then we're isolating for x. You can cancel out using logarithms because of the properties of logarithms that we've looked at previously. And because we're doing it to both sides, we're technically not changing the equation, even though, again, it looks like it. But in terms of solving equations, as long as we do the same thing to both sides, we haven't really changed it, even though it looks different. So we have a couple more. We have 6 other equations to solve using logarithms. Going to pause the video and let you try these on your own. It's very similar in terms of the ones we just did. Same idea. I don't think there's anything too tricky in terms of solving them. Right? It's still the same idea. Set a logarithm to both sides. In some cases, maybe D, you might have to do something a little bit extra first, right, to get the power alone, similar to the example that we just did. But I would recommend pausing the video, trying to solve these using logarithms on your own, solve for what x is, and then we'll come back with the full solution. So again, pause the video now to try these on your own, and we'll come back with the solutions. So coming back to these questions, we have our full solutions. And so we'll just take a look at them and go through them. So for A, again, set logs to both sides. So log 7 to the power of 2x equals log of 3.5. Again, the exponent comes down in front thanks to the exponent rule, and we work to cancel out or isolate x. Right? We divide by log 7 to both sides because those are just numbers. And then we divide both sides by 2 to get x alone. B, same idea. Even though the base is a fraction, we can still set logs to both sides. The exponent comes down, and we divide out our logs, and then work to isolate x. Right? A little bit more work here because our exponent is 3x minus 2. It's not just x or 3x. Right? We have an additional term there. For C, again, same idea, more basic, similar idea, set log to both sides, bring the exponent down, and isolate for x. C, even though it's written differently with the exponent on the left or the right side, it's still the same idea. If it helps, you can switch the entire 2 sides, right? You can switch both of these. And put 1.04t is equal to 2 if it helps, if you prefer it that way. Otherwise, just leave it as is and solve how you normally would. Set log to both sides, bring the exponent down, divide out and isolate for your variable. D, as I mentioned, was one that might be a little bit different because we don't have the power alone on the right side. So we do have to divide out 50 first. We can't multiply 50 by 1.04 because that would be combining two different powers, so to speak. Right? You could think of the 50 as being 50 or a power of 50 to the power of 1, and then we have 1.04 to the power of t, right? So those are two different bases, so we can't combine them. But I can divide by 50 to cancel it out, divide the other side by 50, and get 8 equals 1.04 to the power of t, and then we use our logarithms to help cancel out those bases and isolate for t. And then E again is similar to other ones that we've done. So nothing too new. It's just kind of getting used to working through these steps. That's something that we haven't quite done before, right? So this is a little bit different. You probably haven't seen logarithms before, but we're working through and trying to cancel or use them to help us solve our exponential functions. So now, given an exponential function, we should be able to solve for the variable regardless of whether we can get common bases or not. Right? So if you think of all the questions we did in the previous unit, we were always able to solve using common bases. Or if we didn't, we learned how to use technology. But this is now the hands-on way where we can solve the exponential functions. So now we can kind of expand the numbers that we deal with because we don't have to worry so much about the common bases. So again, the main thing from this lesson is just make sure we're familiar with these steps, right? Take the log of both sides, use the exponent rule of logs, and then isolate for x. So that's the main thing you should be kind of carrying forward from this lesson.